66 million years ago, something ended. The precise moment is lost to deep time, but the evidence remains. There is a thin layer of iridium-rich clay pressed between rock strata scattered across every continent. Above that line are fossils of creatures that ruled Earth for over 160 million years. Below it, there is silence. For most of human history, we have understood this boundary as absolute. The age of dinosaurs ended. The age of mammals began. The story seemed finished. But evolutionary history does not observe the clean chapter breaks we prefer. Life does not pause to let one era end before another begins. And the more scientists examine what survived that day, the more complicated the story becomes. This is not because the evidence is unclear, but because the question itself was never as simple as we assumed. When you picture a dinosaur, you are probably seeing something specific: a massive reptile, scales catching sunlight, and feet shaking the ground with each step. Tyrannosaurus rex, Triceratops, Brachiosaurus. These are the images museums built into our collective memory. They are the creatures that define what dinosaur means in the popular consciousness. And yes, those animals are gone. No Tyrannosaurus stalks through modern forests. No Triceratops grazes in hidden valleys. If that is the question, whether those specific animals still walk the earth, the answer is clear. But science asks different questions. It asks about lineage. It asks about evolutionary continuity. It asks about what it actually means for something to survive, not just as an individual or even a species, but as a living branch on the tree of life. When you frame the question that way, when you follow the evidence without preconceptions about what should or should not have endured, you arrive somewhere unexpected. This is a story about survival, but not the kind you might imagine. There are no lost worlds and no isolated populations of sauropods waiting to be discovered. Reality, as it often does, offered something more subtle and more profound. It is a twist that scientists have spent decades confirming through fossil evidence, genetic analysis, and anatomical comparison. It is a story about how catastrophe does not always mean total erasure. It is about how evolution finds paths through even the most devastating bottlenecks, and how the descendants of ancient creatures can become so transformed that we stop recognizing them for what they are. The asteroid that struck the Yucatan Peninsula 66 million years ago did not discriminate. It did not choose which species deserved to continue and which should end. What it created were conditions, both immediate and prolonged, that made certain traits suddenly valuable and others catastrophically inadequate. Size became a liability. Dietary specialization became a death sentence. But flexibility, small body mass, and one particular feature that had evolved tens of millions of years earlier for entirely different purposes, these became tickets through the narrowest of evolutionary doorways. The question is not whether dinosaurs still exist. The question is whether you would recognize a dinosaur if you saw one today, standing on your windowsill or walking across your lawn. Whether survival counts if the survivors look nothing like what came before. Whether a lineage that bent rather than broke, that adapted rather than died, deserves to be called by its ancestral name. What follows is not speculation or fringe theory. It is the consensus view of paleontology, evolutionary biology, and comparative anatomy. It is a conclusion built from thousands of fossils, genetic sequences, and anatomical comparisons. It is a story that begins with the most studied extinction event in Earth's history and ends, improbably, with the most diverse group of land vertebrates alive today. It asks you to reconsider what extinction really means when the line between ending and transformation turns out to be far blurrier than the boundary layer in those ancient rocks. The asteroid fell, the world burned, and in the aftermath, among the survivors struggling through a planet rendered almost unrecognizable, were the ancestors of something you will see tomorrow. The phrase, "dinosaurs are extinct," is taught in elementary schools, displayed in natural history museums, and repeated so often it feels like geological fact. For generations, it has been the clearest example we have of total evolutionary termination. It describes a once dominant group that simply ended. Children learn this alongside the alphabet. Adults accept it without question. The age of dinosaurs lasted from 252 to 66 million years ago. It is seen as a closed chapter in the biography of Earth. But that certainty rests on something we rarely examine. It depends on what we mean when we use the word dinosaur. The word itself carries weight beyond scientific classification. It conjures specific images and implies specific forms. When most people hear the word, they do not think of a category. They think of creatures. They imagine enormous reptiles with scales and massive bodies. They see animals fundamentally different from anything walking the planet today. That is the cultural inheritance of the word, built from a century of museum reconstructions, film depictions, and childhood fascinations. Scientists, however, use the term differently. In paleontology and evolutionary biology, Dinosauria is not a collection of monsters from the past. It is a clade. This is a branch on the tree of life, defined by common ancestry and shared characteristics. It includes every animal descended from the most recent common ancestor of Triceratops and modern birds, along with all descendants of that ancestor. That definition is precise, testable, and based on anatomical evidence. It is also considerably broader than the popular imagination allows. This creates a strange disconnect. When someone asks if dinosaurs still exist, they are usually asking about a specific mental image. Could a Tyrannosaurus or a Stegosaurus still be alive somewhere, hidden in an unexplored jungle or a deep lake? That is a reasonable question with a clear answer. But it is not the only question the words can ask. There is another interpretation that scientists grapple with. Does the evolutionary lineage we call Dinosauria still have living representatives? That question opens different doors entirely. The challenge is that extinction and survival are not always binary states. Lineages do not simply vanish or continue unchanged. They transform, they adapt, they split into new forms that may bear little resemblance to their ancestors. A family tree does not end just because the individuals on one branch stop looking like the individuals on another. Evolutionary continuity operates through descent with modification. Sometimes the modifications are so profound that we stop recognizing the connection. Consider what it means for something to still exist in an evolutionary sense. If a group of animals survives a catastrophic event but evolves dramatically in response to new environmental pressures, does the original group still exist? If the descendants retain fundamental elements of the same skeletal architecture and reproductive strategies, but look entirely different on the surface, do they count as survivors? Science would say yes. Popular understanding often says no. The gap between those answers is where this story lives. The creatures that dominate our mental landscape when we think of dinosaurs did vanish. There is no ambiguity there. No Tyrannosaurus rex has walked the earth for 66 million years. No Brachiosaurus has browsed treetops in recorded history. No Triceratops has left tracks in modern sediment. Those specific animals, those specific body plans, and those specific ecological roles are extinct. The evidence is overwhelming, and the scientific consensus is clear. But Dinosauria as a clade, as a branch of the evolutionary tree, is a different matter entirely. That is the question this story actually explores. We are not asking whether the dinosaurs of museum dioramas still roam hidden corners of the world. We are asking whether the lineage they represent ever truly ended. We are looking at whether survival can occur through a transformation so complete that the survivors become unrecognizable. The answer requires us to follow evidence backward through time and forward through evolution. It asks us to trace anatomical features across millions of years of change. It demands that we set aside what we expect dinosaurs to look like and focus instead on what defines them scientifically. And it forces us to confront a difficult truth. Sometimes the most dramatic survival stories are the ones we overlook, because the survivors no longer match our mental images of what should have endured. What happened 66 million years ago was not just an ending. For certain lineages, it was also a test. It was a test that a specific group of dinosaurs persisted through, aided by a combination of existing adaptations and sheer circumstance. The story of what came after does not diminish the extinction. It does not make the loss any less catastrophic, but it does complicate the narrative of total termination we have carried for so long. Before we can understand what survived, we need to understand what happened. We must look at the event itself, the devastation it caused, and why the word extinction seemed, for so long, like the only possible conclusion. The rock was approximately 10 kilometers across. By cosmic standards, it was unremarkable. It was a fragment of debris orbiting the Sun among countless others, following a path that had likely remained stable for billions of years. But trajectories change, gravitational influences accumulate, and 66 million years ago, the path of that particular asteroid intersected with the orbit of the Earth at precisely the wrong moment. It struck what is now the Yucatan Peninsula in Mexico, near the modern town of Chicxulub. The impact released energy equivalent to billions of nuclear weapons detonating at once. This is not a metaphor, but the closest comparison we have to that scale of force. The asteroid punched through the atmosphere in seconds. It moved too fast for the air to move aside. When it hit, it vaporized instantly, along with thousands of cubic kilometers of rock beneath it. The crater formed in minutes. Bedrock liquefied. Molten material fountained upward and outward. The ground behaved like a fluid, rippling in concentric rings that would solidify into formations geologists can still map today. Even after 66 million years of erosion and sediment burial, the Chicxulub crater remains visible in gravitational and magnetic surveys. It is a scar 150 kilometers wide, marking the point of impact. But the crater itself was only the beginning. What followed was a cascade of connected catastrophes. Each fed into the next, creating conditions that were incompatible with most forms of life then existing on Earth. Scientists have spent decades reconstructing what those first hours, days, and years looked like. The picture that emerges is almost incomprehensibly hostile. The immediate shockwave flattened everything for thousands of kilometers. Forests ignited instantly. Animals were killed by the pressure wave alone. Their bodies were torn apart before the flames ever reached them. Earthquakes measuring beyond any modern scale rippled across tectonic plates. The impact triggered massive tsunamis. These were not the kind that strike coastlines today, but walls of water that scoured continents. They reached hundreds of kilometers inland before finally retreating. Within hours, ejected material began falling back to Earth. Rock, vaporized by the impact, had been launched into the upper atmosphere and beyond. As it descended, friction with the atmosphere heated it until it glowed. Evidence suggests that global temperatures may have spiked significantly. Some models propose that surface fires ignited across many continents, even those untouched by the initial blast. Animals caught in the open had nowhere to shelter. Even creatures in burrows or underwater faced rapidly rising temperatures. Then came the darkness. Pulverized rock, soot from worldwide fires, and sulfur compounds from vaporized minerals filled the atmosphere. Sunlight, which had nourished the ecosystems of the Earth for billions of years, could not penetrate the haze. Estimates suggest the sky remained dark enough to halt photosynthesis for many months, or by some accounts, over a year. Plants died. Without plants, the herbivores starved. Without herbivores, the carnivores followed. Food chains did not just break, they collapsed entirely. The term scientists use for this period is the impact winter. Temperatures plummeted. The same atmosphere that had burned became a barrier against heat. Climate simulations suggest global temperatures could have dropped by as much as 28 degrees Celsius in some regions. Creatures adapted to the warm, stable climate of the late Cretaceous found themselves in conditions resembling polar winters. They had to face this without the gradual seasonal transitions that allow for adaptation or migration. Acid rain followed. Sulfur compounds in the atmosphere combined with water vapor. This created precipitation corrosive enough to damage plant tissue and poison freshwater systems. Ocean chemistry changed rapidly. The pH levels shifted. Marine ecosystems, already stressed by temperature changes and the loss of sunlight, faced additional chemical disruption. Coral reefs died. Plankton populations crashed. The foundation of marine food webs disintegrated. This was not a brief catastrophe. The initial violence lasted minutes. The thermal pulse lasted hours. But the aftermath stretched for years and possibly decades. Even after the dust settled and the sunlight returned, the world that re-emerged was fundamentally different. Ecosystems that had taken millions of years to establish were gone. The rules that had governed survival for the entire Mesozoic era no longer applied. The fossil record marks this moment with unusual clarity. Geologists call it the KPG boundary. This is the thin layer of sediment separating the Cretaceous period from the Paleogene period. Below that boundary, there are abundant dinosaur fossils representing dozens of species across multiple continents. Above it, there is almost nothing. The disappearance is so abrupt and so geographically widespread that it can only be explained by a sudden, global catastrophe. Scientists estimate that approximately 75% of all species on Earth went extinct during this event. Dinosaurs are the most famous victims, but entire groups across every major habitat perished. Marine reptiles like mosasaurs and plesiosaurs vanished. Flying pterosaurs, which had ruled the skies for 160 million years, disappeared completely. Ammonites, the shelled creatures that had diversified into thousands of species, went extinct in their entirety. Many plant species died out. Entire families of mammals, lizards, and amphibians vanished. The non-avian dinosaurs were among the most comprehensive casualties. These were the creatures that populated our mental landscape of the Mesozoic. The massive sauropods that had evolved to browse treetops are extinct. The armored ankylosaurs built like living tanks are extinct. Ceratopsians with their elaborate horns and frills are extinct. The tyrannosaurs, apex predators that had dominated for millions of years, are gone. Hadrosaurs, pachycephalosaurs, and ornithomimids all vanished. Every large land dinosaur species, every niche they filled, and every adaptation they developed was terminated. The selectivity of the extinction offers clues about what determined survival. Large animals died in the greatest numbers. Creatures requiring a substantial daily food intake could not endure the prolonged famine. Specialists adapted to specific diets or habitats had no flexibility when those resources vanished. Animals with slow reproductive rates could not recover from population crashes. The world after the impact favored small size, dietary flexibility, and the ability to survive on minimal resources for extended periods. But the evidence also shows that the extinction was not total. The boundary layer is not a wall, it is a filter, and some things pass through it. Small mammals survived. These were creatures that could burrow, subsist on seeds or debris, and had metabolisms capable of enduring cold and scarcity. Some reptiles made it through, particularly crocodilians and certain lizard groups. Amphibians survived with surprisingly high success rates. Their ability to enter dormancy and their ties to freshwater environments helped them weather the storm. Insects, resilient and adaptable, also persisted. The communities on the ocean floor, which were less dependent on photosynthesis, remained largely intact. And in one specific corner of the dinosaur family tree, something else survived too. Among a group of small, feathered theropods that had already been evolving for tens of millions of years, a few lineages endured. They were not many species, and they were not the dominant forms, but they were enough. They were just barely enough to carry forward a lineage that would, eventually, radiate into something new. The world that emerged from the KPG extinction was emptier and darker. It was structured entirely differently than what came before. But it was not lifeless. The survivors struggled through a planet that no longer resembled the one their ancestors had known. Yet they carried with them the raw material for recovery. What happened next would redefine what it meant to be a dinosaur. The world that existed on the other side of the KPG boundary was unrecognizable. The ecosystems that had defined the Cretaceous were gone. The towering forests, the vast herds of herbivores, and the complex relationships between predator and prey had vanished. What remained was a planet in recovery. Its biological communities were reduced to whatever had managed to endure months or years of darkness, cold, and starvation. Survival was not random. The fossil record shows clear patterns in what made it through and what did not. Size mattered enormously. Animals weighing more than 25 kilograms had drastically reduced survival rates. The logic is straightforward. Larger bodies require more food more consistently. When primary productivity collapsed and food chains disintegrated, creatures that needed substantial daily intake simply could not find enough to eat. Starvation was almost certain for anything above that weight. Small mammals were among the most successful survivors. These were not the specialized mammals we see today. Those would evolve later, filling the niches left vacant by the extinction. The mammals that made it through were generalists. They were creatures that could eat seeds, insects, plant matter, or carrion. Many were burrowers, which offered two crucial advantages. Underground refuges provided insulation against extreme temperatures, both the initial thermal pulse and the subsequent impact winter. And animals that could retreat below ground could wait out the worst conditions by lowering their metabolic demands when food was scarcest. Certain reptile groups also persisted. Crocodilians made it through, likely due to their semi-aquatic lifestyle and their remarkable ability to survive long periods without food. Modern crocodiles can go months between meals, a trait their ancestors almost certainly shared. Lizards and snakes survived in reduced numbers, particularly smaller species with flexible diets. Turtles also showed high survival rates. Their slow metabolisms and ability to enter dormancy served them well during the prolonged environmental crisis. Amphibians survived with surprisingly high success rates. Many of their life cycles include stages that can tolerate harsh conditions. Eggs and larvae can pause development, while adults can burrow into mud and reduce their activity. Freshwater systems recovered more quickly than those on land. Decomposing organic matter provided nutrients for insects, which in turn fed amphibians emerging from dormancy. Insects weathered the catastrophe remarkably well. Their small size and short generation times meant that populations could recover quickly once conditions improved. Many insects can survive as eggs or pupae for long periods. Others fed on the dead organic matter that was abundant in the aftermath of the impact. While the insect record shows some disruption, it was not the near-total extinction seen in larger animal groups. In the ocean, the situation was more complex. Surface ecosystems collapsed as plankton populations crashed. This removed the foundation of the marine food web. However, deeper ocean communities remained largely intact. These were life forms that relied on chemical energy rather than sunlight. Some fish groups and sharks also managed to persist. Marine invertebrates that could tolerate low oxygen or feed on debris had better odds of survival. Plants also showed clear patterns of resilience. Ferns bounced back so quickly that geologists call this period the fern spike. Fern spores can remain dormant for years and travel far on the wind. Once sunlight returned, they rapidly covered the devastated landscape. Flowering plants also showed resilience. Many produced seeds that could remain viable for long periods under harsh conditions. But there is one detail that matters most for our story. Among these survivors were members of one particular dinosaur lineage. These were not the giants or the dominant forms. They were small theropods, likely weighing less than 1 kilogram. They were feathered. This was a trait that had evolved in dinosaurs tens of millions of years before the impact, originally serving as insulation or for display rather than flight. Evidence suggests these survivors were already capable of powered flight, or at least climbing and gliding. Flight itself did not save them, as many flying reptiles went extinct, but the traits associated with flight were vital. Small size meant lower food requirements. Feathers provided warmth during the impact winter, and the ability to move through three-dimensional space offered access to resources that ground-dwelling animals could not reach, like seeds in tree bark or insects in hidden crevices. These dinosaurs were not thriving. Their populations likely crashed just as dramatically as other groups. They were not immune to the catastrophe, but they did not go extinct. A handful of lineages made it through the boundary. Exactly which species survived is still debated, as the fossil record from that time is sparse. But all the scientific evidence points to a narrow survival. A tiny fraction of the avian dinosaur lineage passed through this evolutionary bottleneck. This is where the story pivots. The extinction that killed the Tyrannosaurs failed to eliminate this one particular branch. This was not due to any inherent superiority. They were not better designed or more advanced. They survived because they happened to possess a combination of traits that proved valuable in a devastated world. These were traits that had evolved for entirely different reasons millions of years earlier. The planet these dinosaurs inherited was nothing like the one their ancestors had known. The Cretaceous had been warm and lush. The early Paleogene was colder and emptier. The rules of survival had changed completely. In this transformed world, with competition reduced and new opportunities emerging, these small, feathered survivors began to evolve. What happened next was not inevitable. Evolution does not follow a set path. But with vast, empty niches and millions of years to diversify, these dinosaur survivors grew into new forms. They populated nearly every habitat on Earth. They evolved new body plans and new behaviors. They became so different from their ancestors that for most of human history we did not recognize the connection at all. The bridge between those survivors and what exists today is not speculation. It is written in fossils, in anatomy, and in genetic sequences. Understanding that bridge means understanding what a dinosaur actually is. It means looking at what defines the lineage scientifically, rather than what we expect it to look like. The connection between dinosaurs and birds is not a recent discovery, though it took science more than a century to fully accept it. The first hints appeared in 1861, just 2 years after Darwin published On the Origin of Species. Workers in a limestone quarry in Bavaria uncovered something extraordinary. It was a fossil with the skeleton of a small dinosaur and the unmistakable imprint of feathers. They named it Archaeopteryx, from the ancient Greek words for ancient wing. Archaeopteryx was a mix of features that should not have coexisted, at least not according to the understanding of that time. It had wings and feathers like a bird, but it also had teeth, a long bony tail, and clawed fingers extending from its wings. The skeleton looked reptilian, while the plumage looked avian. For decades, scientists debated what it meant. Today, many researchers view it as a transitional fossil that blurs the line between groups. This leads scientists to debate whether it was a primitive bird or a highly bird-like dinosaur. The debate simmered for over a century. It was constrained by incomplete fossil evidence and the difficulty of tracing evolutionary relationships before modern methods existed. But starting in the 1960s and accelerating dramatically in the 1990s, new discoveries began filling in the gaps. Fossil sites in China, preserved in fine volcanic ash, yielded specimens with unprecedented detail. What they revealed was unambiguous. Feathers were not unique to birds. They appeared throughout the theropod dinosaur lineage. Sinosauropteryx, discovered in 1996, was a small carnivorous dinosaur clearly related to Tyrannosaurs, but it was covered in a coat of simple, filament-like feathers. Microraptor, found in 2003, had 4 wings. It had flight feathers on both its forelimbs and hind limbs, suggesting a way of moving completely unlike modern birds. Anchiornis, described in 2009, showed a full covering of aerodynamic feathers, despite being anatomically a dinosaur by any traditional definition. These were not isolated oddities. Feathered dinosaur fossils emerged from multiple sites, spanning different time periods and representing different branches of the family tree. The pattern became impossible to ignore. Feathers evolved in dinosaurs, not in birds. Birds inherited feathers from their dinosaur ancestors. The trait appeared at least 50 million years before anything we would recognize as a modern bird existed. This means feathers originally served purposes that had nothing to do with flight. Scientists now believe early feathers functioned primarily as insulation to help small theropods maintain body temperature. Later, they likely played roles in display, such as visual communication or mate attraction. The fossil record preserves evidence of coloration patterns in some specimens, suggesting feathers were patterned and possibly quite elaborate. Only later, as certain lineages developed longer feathers and began experimenting with movement through the air, did flight become possible. Feathers were a pre-adaptation. They were a feature that evolved for one purpose and later became essential for another. But feathers are just the beginning. The anatomical connections between theropod dinosaurs and modern birds extend through virtually every major skeletal system. Consider the wishbone, the familiar forked bone found in bird skeletons. Most people assume it is unique to birds, but it is not. The wishbone is formed from fused collarbones, and it appears throughout the theropod dinosaurs. Tyrannosaurus rex had a wishbone, Velociraptor had a wishbone. It is a dinosaur trait that birds retained, not a bird trait that appeared spontaneously. The leg and foot structure tells the same story. Birds walk on their toes with the heel elevated. This posture might seem unusual until you realize it is standard theropod anatomy. The three forward-facing toes and the arrangement of the foot bones all match the dinosaur pattern. When you watch a chicken walk, you're watching the same basic mechanics that a small theropod dinosaur would have used 100 million years ago. Bird bones are hollow and filled with air sacs. This makes the skeleton lighter, which benefits flight. But these hollow bones were not invented by birds. They are found in many different dinosaur groups. Birds simply kept and refined a feature their ancestors had already developed. Evidence from skeletal structures strongly implies that many theropod dinosaurs possessed a system of air sacs. This suggests a respiratory efficiency that may have led to the one-way airflow found in birds today. Even reproductive biology shows the connection. Birds lay hard-shelled eggs, incubate them with body heat, and engage in parental care. All of these behaviors appear in the dinosaur fossil record. Fossilized nests have been found, with adult dinosaurs positioned over eggs in brooding postures identical to modern ground-nesting birds. The egg itself follows the same basic pattern shared by dinosaurs and their descendants. The hand structure requires closer attention because it is both crucial and often misunderstood. Modern bird wings do not look like hands. The bones are highly modified, fused in some places and reduced in others. While the specific path of this change remains a subject of intense research, fossil analysis suggests a clear lineage. The dinosaur hand was modified into the structural support for the bird wing. This did not happen by adding new structures, but by changing existing ones. The skull shows perhaps the most dramatic transformation, yet the connection remains traceable. Early birds like Archaeopteryx had toothed jaws and a reptilian skull. Later forms lost the teeth and developed beaks. These were lightweight structures better suited to flight. But the bones themselves and the way the jaw connects still retain clear ties to dinosaur anatomy. The beak is not a replacement for a dinosaur skull. It is a modification of it. This is where modern analytical methods become essential. Scientists use cladistics to analyze evolutionary relationships based on shared characteristics. By examining hundreds of features across dozens of species, researchers construct family trees that show how organisms are related. When you apply this analysis to birds and dinosaurs, the result is clear. Birds sit within the group called theropoda. They are not just descended from dinosaurs, they are dinosaurs in the same way that bats are mammals and snakes are reptiles. This is not a matter of interpretation. The consensus among scientists is overwhelming. Birds are avian dinosaurs. The creatures we traditionally call dinosaurs, the ones that went extinct 66 million years ago, are more precisely called non-avian dinosaurs. The terminology matters because it reflects actual relationships, not just superficial appearances. Intriguing studies have sought to reinforce this conclusion from a molecular angle. Some researchers have reported extracting protein fragments from Tyrannosaurus rex fossils that appear to align more closely with birds than any other living group. While this is still debated, the evidence supports what anatomy already indicated. Birds and non-avian dinosaurs share an immediate common ancestry. This creates a peculiar situation. We have a word, dinosaur, that in popular usage means an extinct giant reptile. But in scientific usage, it means a member of a specific branch of life that includes modern birds. Those two definitions lead to very different answers to the question of whether dinosaurs still exist. By the popular definition, the answer is no. By the scientific definition, the answer is absolutely. Understanding this distinction does not diminish the extinction event. It does not mean Tyrannosaurus rex is somehow still alive. What it means is that one branch of the family tree survived through a combination of traits that prove valuable. That branch continued evolving for the next 66 million years. The survivors transformed so completely that we stopped recognizing them for what they were. But transformation is not extinction. It is evolution. The birds around us today carry within their bodies the legacy of their dinosaur ancestry. Every time a bird walks, that is dinosaur locomotion. Every time a bird breathes, that is a respiratory system inherited from ancient ancestors. Every time a bird lays an egg, that is a biology unchanged in its fundamentals for over 200 million years. The packaging looks different, and the scale has changed, but the underlying architecture remains. What this means is that dinosaurs did not vanish. They adapted. And what they adapted into is the most diverse and successful group of land vertebrates currently living on Earth. There are approximately 10,400 species of birds alive today. That number fluctuates as new species are discovered and others are reclassified, but the scale remains consistent. Birds represent the most diverse group of land vertebrates currently living on Earth. They are more diverse than mammals, they are more diverse than reptiles or amphibians, and every single one of those species is, by the standards of modern science, a dinosaur. This is not a metaphor or poetic license. It is a classification based on evolutionary descent. When scientists refer to birds as avian dinosaurs, they are using the same logical framework applied to every other organism. Humans are apes because we share a common ancestry with chimpanzees and gorillas, and we possess the defining characteristics of that group. Whales are mammals because they evolved from land-dwelling mammals and kept their mammalian traits despite adapting to life in the ocean. Birds are dinosaurs because they evolved from theropod dinosaurs and retain the fundamental characteristics that define that lineage. Walk outside and observe the birds around you, whether they are sparrows, crows, or pigeons. What you are seeing is not an animal that replaced the dinosaurs. You are looking at a living theropod. You are seeing a direct continuation of a lineage that extends back over 230 million years. The body you are observing has been shaped by the same evolutionary forces that shaped Velociraptor, Allosaurus, and Tyrannosaurus rex. The differences are real and significant, but they are modifications of a shared ancestral blueprint. Consider feathers again in their modern context. Every bird species possesses them, from the massive ostrich to the tiny hummingbird. The structure varies, including flight feathers, down feathers, and bristles, but the fundamental architecture remains consistent with what appears in the fossil record. Modern feathers grow from follicles in the skin. They consist of a central shaft with barbs branching off and barbules that interlock to create a continuous surface. This exact structure appears in fossils like Microraptor and Anchiornis. These fossils are preserved in such detail that scientists can analyze the pigment-containing structures and reconstruct their original colors. Feathers serve multiple functions in modern birds, just as they likely did in their dinosaur ancestors. Insulation remains crucial. Down feathers trap air and maintain body temperature, which is essential for animals with high metabolic rates. Display also continues to matter. Many bird species have elaborate plumage used in courtship and social behavior. And flight, the function we most associate with feathers, depends on precisely structured flight feathers with asymmetrical shapes that generate lift. The skeletal system tells an equally clear story. Bird skeletons are theropod skeletons. modified for flight and other specialized behaviors. The hollow bones filled with air sacs, the fused collarbones forming the wishbone, and the arrangement of the pelvis all match the theropod pattern. When paleontologists discover a new theropod fossil, they use bird skeletons as references because the connections are so direct. Look at the foot of a bird, particularly a chicken or other ground-dwelling species. There are 3 forward-facing toes, each ending in a claw. The ankle joint is elevated off the ground, creating a leg structure that appears to bend backward. This is actually the ankle, not the knee. This is digitigrade locomotion, and it is identical to what the ancient theropods used. The specific arrangement of bones and joints matches dinosaur anatomy so precisely that you can overlay the 2 structures and see the direct link. Even in birds that have lost the ability to fly, the dinosaur heritage remains obvious. Ostriches, emus, and cassowaries are among the largest birds alive. Their anatomy showcases features that connect directly to their ancestry. They have large bodies supported on powerful legs. They have reduced wings that no longer function for flight, but keep the skeletal structure of theropod forelimbs. Their long necks have vertebrae arranged in a characteristic S-curve. These flightless forms provide a vivid window into how certain dinosaur traits have adapted for the modern world. Reproductive strategies provide another layer of evidence. Birds lay hard-shelled eggs, a trait they share with all dinosaurs. But the specific details, such as nest construction, incubation behavior, and parental care, all appear in the fossil record of non-avian dinosaurs. Fossilized nests show eggs arranged in patterns consistent with modern ground-nesting birds. Some specimens even preserve adults positioned over nests in brooding postures, with their forelimbs spread over the eggs to protect them. The discovery of a dinosaur called Sitipati demonstrated that complex parental care existed long ago. The specimen was found fossilized while protecting its nest. It died while incubating, probably during a sandstorm, and was preserved in a position identical to modern birds. Its forelimbs were extended to cover the nest, shielding the eggs from the elements. This is a case of direct behavioral continuity across 75 million years. Behavioral evidence extends beyond reproduction. Many bird species are highly social. They form flocks, communicate with sounds, and engage in complex displays. Fossil evidence suggests similar behaviors in non-avian theropods. Trackways show multiple individuals moving together, suggesting group behavior. Bone beds containing numerous individuals of the same species indicate social groups that lived and died together. Vocalization is harder to study in fossils, but clues exist. While the specific sound organ of a bird has not been found in ancient fossils, researchers believe these dinosaurs were capable of a range of sounds. The anatomical evidence of their hearing and social structures suggests that sound production was important in their behavior, just as it is for birds today. Feeding strategies also show a mix of continuity and change. Early theropods were mostly meat-eaters, and many modern birds maintain that pattern. Raptors hunt, herons fish, and kingfishers catch aquatic prey. But birds have also evolved to eat plants, seeds, nectar, and insects. This flexibility likely played a role in their survival during the mass extinction. The ability to shift diets when preferred foods became unavailable helped early avian dinosaurs survive and later diversify into every available ecological niche. The beak is one of the most significant innovations in bird evolution. Modern birds lack teeth, having lost them over millions of years. Instead, they have beaks made of keratin that are specialized for different tasks. such as crushing seeds or tearing meat. This diversity of beak forms is a clear example of how a single group can change to use different resources. But beneath the beak, the underlying skull still reflects the architecture of a dinosaur. The respiratory system is also clearly linked to dinosaur ancestry. Birds have the most efficient respiratory system of any vertebrate. Air flows in one direction through the lungs, which means oxygen is extracted during both inhalation and exhalation. This system depends on air sacs distributed throughout the body, some of which extend into the hollow bones. This reduces weight while maintaining strength, which is crucial for flight. This feature is not unique to birds. It appears throughout dinosaur lineages, including the massive, long-necked sauropods. This suggests that the efficient respiratory system seen in modern birds evolved gradually. Flight did not create these hollow bones. Instead, it took advantage of a system whose foundations likely began with the earliest ancestors of the dinosaurs. The global distribution of birds shows how successful this lineage has been. Birds inhabit every continent, including Antarctica. They have adapted to environments from the Arctic tundra to tropical rainforests and open oceans. They have evolved body sizes ranging from the bee hummingbird at less than 2 grams to the ostrich at over 150 kilograms. This extraordinary diversity, all within a single group, represents one of the most successful stories in the history of life. Modern genetic research confirms these connections. By analyzing the DNA of different species, scientists have consistently placed birds within the dinosaur family tree. The genetic similarities between birds and their closest reptilian relatives create a molecular map that matches the evidence from fossils and anatomy. The genome reinforces the story told by the bones. All of this evidence leads to a simple conclusion. Birds are not just related to dinosaurs. Birds are dinosaurs, in exactly the same way that humans are primates. The lineage never ended. It transformed, adapted, and succeeded beyond what might have seemed possible after the Great Extinction. When you see a hawk circling overhead, you are watching a predatory dinosaur hunting. When you hear songbirds in the morning, you are hearing dinosaurs communicating. The creatures that fill our skies and forests are the continuation of an ancient story written in feathers and hollow bones. The question of whether dinosaurs still exist has a clear answer. They exist in numbers that would have seemed impossible 66 million years ago. They have achieved a level of diversity that rivals the richness of the ancient world. They have adapted to a planet that has been utterly transformed, and they have done it by remaining fundamentally what they have always been. They are simply modified, specialized, and successful in ways we are only beginning to understand. The story of the KPG extinction has always been told as an ending. A catastrophic event terminates the age of dinosaurs. The dominant life forms of the Mesozoic vanish. Mammals inherit a planet emptied of its previous rulers. It is a narrative of complete replacement where one chapter closes definitively before another begins. Museums display it this way. Textbooks structure it this way. The popular understanding accepts it this way. But that narrative, while emotionally satisfying and easy to comprehend, oversimplifies what actually happened. Extinction events, even the most severe ones, are not binary switches that turn entire lineages off. They are filters. They are extraordinarily harsh filters that eliminate most life forms but allow certain survivors to pass through. And what passes through carries forward the evolutionary history of everything that came before, even when the survivors look nothing like what we expected. The recognition that birds are living dinosaurs fundamentally changes how we think about mass extinctions. It introduces nuance into a story we thought was straightforward. The non-avian dinosaurs, the familiar giants that populated our films and museum dioramas, did go extinct. That fact remains unchanged. But the broader dinosaur lineage survived through one branch. This branch possessed a combination of chance and pre-existing adaptation. They had the traits necessary to endure conditions that killed everything else in their group. This distinction matters scientifically because it reveals how evolution actually operates during catastrophic events. Natural selection does not plan ahead. It does not preserve species because they might be useful later. Every trait that helped early avian dinosaurs survive, the KPG extinction, evolved for entirely different reasons. They appeared under different selective pressures, in a world that bore no resemblance to the environment after the impact. Small body size evolved for reasons unrelated to surviving a global winter. Feathers evolved for insulation and display, not for providing warmth during an impact winter. Dietary flexibility emerged through normal ecological competition, not in preparation for mass starvation. Yet when catastrophe struck, these pre-existing traits suddenly became crucial for survival. This is what evolutionary biologists call exaptation. These are features that evolved for one purpose but later proved useful for something entirely different. The avian dinosaurs that survived did not endure because they were superior or more advanced. They survived because they happened to already possess characteristics that aligned with the new survival requirements. A different asteroid, striking at a different time, creating different environmental conditions, might have favored completely different traits. It might have allowed completely different lineages to persist. This reframes how we understand evolutionary resilience. Lineages do not survive catastrophes by being strong or dominant. They survive by being flexible. They survive by possessing traits that remain useful across radically different environments. They survive by having enough variation within their populations so that some individuals can tolerate conditions that kill most of their species. The massive non-avian dinosaurs were superbly adapted to Cretaceous ecosystems. That specialization became a liability when those ecosystems collapsed. The small, generalized avian dinosaurs were less specialized. They were less perfectly adapted to any particular niche, and that generalization saved them. The implications extend beyond just dinosaurs. Every major extinction event in the history of the Earth shows similar patterns. During the Permian-Triassic extinction 252 million years ago, approximately 96% of marine species disappeared, but the survivors, the 4% that made it through, carried forward evolutionary lineages that would later diversify and fill the emptied world. The marine reptiles of the Mesozoic, the early dinosaurs, and the first mammals, all descended from species that survived the Permian catastrophe. They often survived in forms that would have seemed insignificant compared to the dominant life forms that perished. This creates a different way of thinking about what extinction means. When we say the dinosaurs went extinct, we are making a statement that is technically true but fundamentally misleading. Non-avian dinosaurs went extinct. The dinosaur lineage did not. The distinction seems small until you realize it changes the entire story. It transforms total termination into radical transformation. It shows that evolutionary history has more continuity than our intuitions suggest. The boundaries we draw between geological periods and evolutionary eras are more permeable than they appear. Modern conservation biology has begun incorporating these insights. When we think about species preservation, we tend to focus on preventing extinction. We try to keep specific organisms alive in their current form. But evolutionary thinking suggests we should also consider lineage preservation. This means maintaining the evolutionary potential within groups that might transform dramatically but continue. A species that evolves rapidly in response to environmental change is not failing to survive. It is surviving in the only way evolution permits. Through adaptation and modification, the dinosaur-bird connection also illustrates how deeply time can obscure relationships. 66 million years is an almost incomprehensible span. Modern humans have existed for roughly 300,000 years. Recorded history spans maybe 5,000 years. The entire period from the KPG extinction to today is more than 200 times longer than the entire existence of our species. Across that duration, evolution had endless opportunities to modify, refine, and reshape the survivors of the extinction. The accumulation of small changes over millions of generations produced organisms that look fundamentally different from their ancestors while keeping the underlying structural blueprint. This is why fossil evidence is so crucial. Without transitional fossils like Archaeopteryx, and without the feathered dinosaur discoveries from China, we might never have recognized the connection. The transformation was so complete that only careful scientific analysis could reveal it, and that suggests something profound. There may be other evolutionary relationships we have not yet recognized. There may be other lineages that survived catastrophes in forms so altered that we have missed the continuity. The emotional response to this realization varies. Some people feel disappointed. They wanted living dinosaurs to mean a Tyrannosaurus rex in the jungle, not sparrows in the garden. That disappointment is understandable. The popular image of dinosaurs carries enormous cultural weight. These creatures represent a specific kind of prehistoric magnificence. Learning that their living descendants are small and common can feel like a letdown. But there is another perspective. This view sees the transformation as more remarkable than simple persistence would have been. A Tyrannosaurus surviving unchanged for 66 million years would be interesting, but it would also represent evolutionary stagnation. It would be a lineage frozen in time while the world changed around it. What actually happened is a more compelling story of life's resilience. One branch of the dinosaur family tree survived the catastrophe and radiated into thousands of new forms. They adapted to environments their ancestors never encountered. They developed capabilities like powered flight, long-distance migration, and complex song. It also changes our relationship with the living world around us. Every bird becomes a window into deep time. The pigeon on your windowsill carries within its body structures refined over hundreds of millions of years. The crow solving puzzles in your backyard is exercising cognitive abilities descended from dinosaur intelligence. The geese migrating overhead are following routes that may have been established when their ancestors were smaller and different, but still fundamentally related to what they are now. The connection makes the everyday extraordinary. This perspective matters for how we think about conservation and environmental change. Birds are not just pleasant additions to ecosystems. They are the living representatives of one of the longest and most successful stories in evolution. They survived the most famous extinction event in the history of the Earth. They adapted to ice ages, continental drift, and sea level changes. They diversified into forms that fill nearly every land-based niche. And now they face challenges created by human activity. Habitat loss, climate change, and pollution threaten to end lineages that have persisted for more than 200 million years. The scientific understanding does not diminish the extinction event. It does not minimize the catastrophe that killed the non-avian dinosaurs. If anything, it makes the survival more remarkable. Knowing how close the avian lineage came to total extinction makes their current success feel more significant. The entire diversity of modern birds stems from a narrow bottleneck of survivors. What happened 66 million years ago was both an ending and a beginning. The forms we think of when we say dinosaur did end. The lineage they belonged to continued, carried forward by creatures different enough that we did not recognize them as dinosaurs for most of human history. That paradox, total transformation within a continuous lineage, is one of the most important lessons of evolution. Life does not survive catastrophe by remaining unchanged. It survives by changing so profoundly that survival itself becomes transformation. The next time you see a bird, you are not looking at something that replaced dinosaurs. You are looking at what dinosaurs became. The difference between those two statements defines how we understand evolution, extinction, and the remarkable capacity of life to persist through circumstances that should have ended it entirely. There is a question that lingers beneath all of this, one that needs to be addressed directly. When most people ask, "Do dinosaurs still exist?" they are not really asking about taxonomic classification or evolutionary lineages. They are asking something more specific. Are there still giant reptiles alive somewhere? Could a Tyrannosaurus or a Brachiosaurus be hiding in an unexplored corner of the planet? Could there be a lost world where the familiar dinosaurs survived, unchanged, waiting to be discovered? The answer, based on all available evidence and biological principles, is no. While impossible is a strong word, the survival of such creatures is considered biologically and ecologically non-viable. Understanding why requires looking at what would actually be necessary for large, non-avian dinosaurs to have survived 66 million years without detection. Start with the most basic requirement: population size. No species survives as a handful of individuals. Biological models suggest that maintaining genetic health typically requires populations numbering in the hundreds or thousands to avoid the collapse caused by inbreeding. Inbreeding depression is the accumulation of harmful genetic mutations in small, isolated populations. This makes long-term survival impossible below certain thresholds. So, we are not talking about one hidden Tyrannosaurus. We are talking about a breeding population large enough to maintain genetic health across millions of years. That population needs food. A large carnivorous dinosaur like Tyrannosaurus would have required enormous amounts of meat daily. Metabolic models suggest that an adult Tyrannosaurus rex could have required the caloric equivalent of a large hadrosaur every few weeks to maintain its massive frame. Scale that up to a viable breeding population, and you are looking at a sustainable prey base numbering in the tens of thousands. Those prey animals need their own food sources, which means vegetation extensive enough to support massive herbivores. You cannot hide an ecosystem of that scale. It would be visible from satellite imagery and aerial surveys. An area capable of supporting such megafauna would show clear signs of their presence. Consider habitat requirements. Large dinosaurs were not subtle creatures. They would leave tracks, break vegetation, create trails, and leave bones when they died. Decades of organized paleontological surveys have covered much of the land surface of the Earth. Remote sensing technology can detect geological features buried underground. Camera traps and satellite tracking have documented even the most elusive modern megafauna. The idea that populations of multi-ton animals could exist anywhere on Earth without leaving evidence detectable by modern technology simply does not hold up. Then there is the fossil record. If large non-avian dinosaurs survived the KPG extinction, we would see their fossils continuing above the boundary layer. We do not. The cutoff is remarkably clean. Dinosaur fossils appear in abundance in Cretaceous strata, then vanish completely in Paleogene deposits. There are no exceptions. There are no Tyrannosaurus bones in rock dated to 50 million years ago, and no hadrosaur fossils from 30 million years ago. This absence is not due to gaps in the fossil record. We have extensive Paleogene deposits from around the world, and they contain abundant fossils of mammals, birds, crocodiles, and fish. There are simply no non-avian dinosaurs. Some people point to cryptozoological reports, such as alleged sightings of living dinosaurs in remote jungles or deep lakes. The most famous is probably Mokele Mbembe, a supposedly sauropod-like creature in the Congo basin. These reports make for entertaining speculation, but they lack the evidence science requires. There are no photographs clear enough for identification, no physical remains, and no verifiable tracks. Crucially, there is no explanation for how a population of 30-ton animals could exist in a region that has been surveyed, mapped, and inhabited by people who would certainly notice something that dramatic. The plesiosaur and mosasaur hypotheses also persist in popular imagination. These were marine reptiles that lived during the Mesozoic, and some speculate they might have survived in deep oceans. But plesiosaurs and mosasaurs were not dinosaurs. They were entirely different reptile groups. More importantly, they face the same survival impossibility as terrestrial dinosaurs. Marine megafauna must surface or come to coastal areas. Modern oceanographic research extensively monitors ocean ecosystems. The idea that breeding populations of multi-ton marine reptiles could exist undetected contradicts everything we know about marine biology. Sometimes the coelacanth is cited as evidence that living fossils can survive undiscovered. The coelacanth is a fish thought to have gone extinct with the dinosaurs until living specimens were found in 1938. But the comparison does not work. Coelacanths are relatively small and live in deep waters in a limited range. Even so, they were eventually found. While they represent a lineage with gaps in their fossil record, their discovery reminds us that small, deep-sea organisms are far easier to overlook than multi-ton land animals. There is also the question of evolutionary stasis. Even if a population of large dinosaurs survived the KPG extinction, it is highly improbable that they would persist in identical form for 66 million years. Evolution does not stop. Populations adapt to changing environments and respond to selective pressures. The idea of a Cretaceous animal remaining unchanged for that long contradicts what we observe in evolutionary biology. Climate change alone would have driven evolution. The world 66 million years ago was warmer, with higher sea levels and different plant communities. Even if some non-avian dinosaurs survived the immediate impact, they would have faced millions of years of ice ages and continental drift. The idea that they would remain frozen in their Cretaceous form while everything around them changed is not how evolution works. The extinction selectivity offers another angle. We know which traits favored survival through the KPG boundary: small size, dietary flexibility, and the ability to shelter or hibernate. Large dinosaurs possessed none of these traits. They were specialized for specific diets and required enormous food intake. They could not shelter effectively. The very characteristics that made them successful in Cretaceous ecosystems made them catastrophically vulnerable when those ecosystems collapsed. So, when people ask about real dinosaurs still existing, they are usually asking whether the giants of the Mesozoic survived. The answer is definitively no. Those specific animals and those ecological roles are extinct. The asteroid impact and its aftermath created conditions fundamentally incompatible with their existence. But here is the important reframing. The question itself reveals a misunderstanding of what makes something real. Birds are real dinosaurs. They are not metaphorical or honorary. They are, by every scientific measure, actual dinosaurs that happen to look different from what we expected. Reality does not adjust to our expectations. Evolution produces what works, not what we find impressive. The cultural image of dinosaurs as massive, reptilian, and extinct is incredibly powerful. We want living dinosaurs to match the museum displays and movie depictions. When science says that living dinosaurs are birds, it may feel like semantics, but it is not. It is an understanding of what dinosaurs actually were beneath the surface. It is a recognition that lineage and evolutionary relationship matter more than appearance. There is also an element of nostalgia in wanting non-avian dinosaurs to still exist. We want the Mesozoic to still be accessible, but that era is 66 million years gone. Its ecosystems vanished and its climate patterns ended. Even if non-avian dinosaurs had survived, they would be living in a completely different world. The Mesozoic we romanticize does not exist anymore. What we have instead is more remarkable than hidden predators would be. We have a lineage that survived total ecosystem collapse and adapted to radically new conditions. They conquered flight and spread across the entire planet. They succeeded so thoroughly that they are now the most diverse group of land vertebrates. That is a better survival story than simple persistence would have been. It shows what life is capable of when pushed to the absolute limits. The dinosaurs matching our cultural expectations are extinct. They died 66 million years ago in a catastrophe that ended entire branches of the evolutionary tree. But the dinosaur lineage survived through the one group that possessed the right combination of traits at the right moment. Those survivors evolved into birds. They are the actual living dinosaurs, the only ones that exist, and the only continuation of a story that otherwise would have ended completely. The search for hidden dinosaurs is a search for a connection to something lost. But that connection exists. It just looks different than we imagined. Every bird is a living link to the Mesozoic, carrying forward structures refined across hundreds of millions of years. Reality, when you understand it fully, is more interesting than the fantasy. Stand outside for a moment and listen. If you hear birdsong, you are hearing something that connects directly to the Mesozoic era. This is not metaphorical, it is not poetic, it is a biological reality. The vocalizations of birds, the structures that produce them, and the behaviors that surround them all have roots extending back through millions of years of evolutionary history. They reach back to a time when their ancestors looked nothing like what we see today. This is the paradox at the heart of the question we started with. Do dinosaurs still exist? By the most common understanding of what that question means, the answer is no. The giant reptiles of the popular imagination are gone. But by the scientific understanding of what dinosaurs actually were, the answer is yes. Unambiguously and definitively, yes. They exist in numbers that would have been unimaginable 66 million years ago. They thrive in forms so diverse that they have adapted to virtually every land-based habitat on Earth. The story of dinosaur survival is not the story most people wanted. There are no hidden valleys where Tyrannosaurus still hunts. There are no isolated islands where sauropods still browse. The catastrophe that struck 66 million years ago was too complete and too global for the large-bodied dinosaurs to survive. Every major branch of the dinosaur family tree died, except for one specific lineage of toothless avian dinosaurs. They were small. They were feathered. By the standards of what came before, they were unremarkable. But they possessed exactly the right combination of traits to endure conditions that killed everything else in their group. They had small bodies that required less food. They had feathers that provided insulation during the impact winter. They possessed a dietary flexibility that allowed them to survive when specialized food sources disappeared. And they had the ability to fly or glide, accessing resources that other survivors could not reach. None of these traits evolved in preparation for a catastrophe. They existed for entirely different reasons, developed under normal pressures in a world that looked nothing like the one that followed the impact. This is how evolution works during mass extinction events. Survival is not a reward for superiority. It is not evidence of a better design. It is a matter of contingency. It is about being in the right place with the right traits at the right time. If there had been a different asteroid or different impact conditions, the survivors might have been completely different. The mammals might have gone extinct. The birds might have died out. Some other lineage we can barely imagine might have inherited the world. But this is the outcome we have. One branch of theropod dinosaurs survived, probably as a handful of species. Their populations crashed and their former diversity was reduced to almost nothing. And then, slowly, over millions of years, they recovered. They diversified. They evolved new forms and new ways of living in a world their ancestors never knew. The ancestors of modern birds lost their teeth and evolved beaks. These were specializations that likely aided their survival during the global food crisis. They refined their flight, they spread across continents, they adapted to forests, grasslands, mountains, and deserts. They became songbirds and raptors, penguins and ostriches, hummingbirds and condors. The transformation was so complete that for most of human history, we did not recognize what they were. We saw birds as their own separate category. It took careful anatomical study, transitional fossils, and eventually genetic evidence to reveal the connection. Birds are not just descendants of dinosaurs, they are dinosaurs. They are the continuation of a story that began over 230 million years ago and never actually ended. This understanding changes the extinction event from a simple ending into something more complex. The KPG extinction was catastrophic. Approximately 75% of all species died. The dominant life forms of the Mesozoic vanished. That devastation is real. But extinction events are not always absolute. They are filters. And what passes through those filters carries forward an evolutionary history in ways that are not always obvious. The recognition that birds are living dinosaurs also changes how we think about time. 66 million years is an almost incomprehensible duration. It is enough time for a small, feathered theropod to evolve into a penguin or a hawk. It is enough time for a single lineage to diversify into more than 10,000 species. That transformation occurred within a continuous evolutionary line. The birds we see today are not new creations that replaced dinosaurs. They are what dinosaurs became. Language often complicates this understanding. The word dinosaur carries cultural baggage. It evokes images of massive bodies and scaly skin. When science says birds are dinosaurs, it conflicts with those associations. It can feel like a redefinition, but the scientific definition came first. The group called Dinosauria was defined based on shared anatomical features documented in the fossil record. Modern genetics have simply confirmed that birds belong within this ancient lineage. The popular image, while compelling, does not reflect what the term scientifically means. This is where the emotional response matters. People often feel disappointed when they learn that living dinosaurs are birds rather than a Tyrannosaurus. That disappointment is understandable. The cultural image of dinosaurs represents a specific kind of prehistoric magnificence. Learning that they survive as sparrows can feel anticlimactic. But there is another way to see this information. The survival and transformation of this lineage is more remarkable than simple persistence would have been. It is a story of resilience and adaptation. It is evidence that evolution does not always follow the paths we expect. It shows that survival can look like transformation, and that a lineage can persist through changes so profound that the descendants become unrecognizable. This also creates a different relationship with the natural world. Every bird becomes more interesting when you understand its deep history. The robin in your garden is a living representative of a lineage that survived the most famous extinction event in history. The crow solving problems in your neighborhood is exercising cognitive abilities refined across millions of years. The hawks, migrating overhead, are following routes that may have been established when their ancestors looked very different. This connection makes the everyday world extraordinary. This perspective matters for conservation. Birds face threats today from habitat loss and climate change that could end a lineage that has persisted for more than 200 million years. They survived an asteroid impact and ice ages, but they are not invulnerable. Evolution gave them tools to survive natural catastrophes, but it did not prepare them for the challenges created by human activity. Species that took millions of years to evolve can disappear in decades if we do not recognize their value. That value is historical. Every bird species represents a continuation of history reaching back through deep time. When a bird species goes extinct, we are not just losing a creature that exists now. We are ending a story that began in the Mesozoic. We are breaking a chain of descent that connects the present to the most famous period in biological history. The question of whether dinosaurs still exist depends entirely on what you mean by the word. If you mean the cultural image of movie monsters and massive reptiles, then the answer is no. Those specific animals are 66 million years gone. Evolution does not repeat itself. The Mesozoic is lost. But if you mean a scientific lineage defined by common ancestry, then the answer is absolutely yes. Dinosaurs exist in extraordinary diversity. They have achieved a level of species richness that rivals the ancient world. They have adapted to a planet transformed beyond recognition, and they have done it by remaining fundamentally what they always were. They are simply modified and successful in ways we did not expect. The next time you see a bird, take a moment to really observe it. Watch how it moves and how its legs articulate. Notice the complexity of the feathers. Listen to its songs. You are not looking at something that replaced the dinosaurs after they went extinct. You are looking at a dinosaur. You are seeing a living continuation of a story that began in the Triassic and survived the most catastrophic extinction event in the last 100 million years. It continues today in forms so successful they have become invisible through familiarity. The age of dinosaurs did not end 66 million years ago. It transformed. It adapted. It survived in the only way evolution permits, through modification so profound that survival itself became transformation. The descendants look nothing like their ancestors, but the lineage persists. Every bird in the sky is evidence that extinction is not always the end of the story. It is just the beginning of a different chapter. It is a chapter that is still being written, and one that you can observe any time you step outside and look up. The dinosaurs are still here. They have just changed in ways we did not anticipate. And that transformation is more extraordinary than simple survival could ever be.